So problem 58 is a nice one for a couple reasons. One, it gives us a chance to play with a definite integral. But the other one is that the U substitution is kind of hinting at stuff that we're going to do in section 8.2. Now, when you're doing a U substitution, you're looking for part of the integral to be the derivative of another part. So in this case, sine is derivative of cosine, and cosine is derivative of sine, up to and including a constant. But in this case, one of these choices is better. Does anyone see what would be a good choice for our U substitution here? I'd do the sine because then you have the cosine that would be the direct derivative of this. So U equals sine of x, du is cosine of x dx. And the nice thing is that you've got your du term already in the integrand. You don't have to solve for anything. So this right here is our du term. So it's going to be the integral of u squared du. Let's also take the time to change our limits of integration. And I think we might see something kind of funny here. So let's see. U of pi is going to be sine of pi. What's the sine of pi? 0. And let's do u of 0. Sine of 0. 0. Are we going to run into some kind of strange result here? Do we really need to proceed with the integration? I mean, not that it's that hard, but do we need to proceed with the integration? What kind of answer are we going to get? 0. Let's see if we can't understand why. If you get an answer of 0, then maybe you should try and make sense out of that. So let's take a quick look at y equals, let's see, do it this way. Sine of x squared times a cosine of x. Might help if I had an x there. There you go. So let's see, between 0 and let's put pi on the map here, pi and 0. Okay. So what's going on that I'm getting a 0 when I do this? Can anyone tell me? Say again? Yeah, so right here at pi over 2, the area between these 2 points and above the x-axis is exactly opposite of this area. So when you add this positive area and this negatively signed area, you're going to get 0. So that's why we're getting such a surprising result here. You're getting 0 when you integrate this. Yes, you'll still get the same answer if you did not change the limits of integration. Yeah, you have to, because the area is still 0, regardless of you change the limits or not. So if you don't change the limits of integration, there's nothing wrong with that. And, you know, perhaps it's just luck that we discovered this earlier than later. But if you don't change the limits of integration, one thing that it's kind of incumbent upon you to do is write like an alpha and a beta here. Because the limits are no longer 0 and pi if you're working in the units of u. 0 to pi was the limits for x, but it's not the limits for u. So what you should do is plug in, you know, some dummy variables or constants or whatever until we get back to the units of x. So this becomes u cubed over 3 between alpha and beta. And then you say, okay, well, this was really just taking the place of sine of x. So then you go back and say, all right, well, that's sine of x cubed over 3. Now I can plug in the original units, 0 to pi. So what happens now? Well, I'll get sine of pi cubed over 3 minus sine of 0 cubed over 3. And it's still going to be 0 minus 0 when we do it that way. So you'll eventually get the same result. So it's a good question, and I appreciate it. I also appreciate the opportunity to make a little speech about this part right here, because you really shouldn't use 0 to pi here, because that's the units for x, not for u. All right. Anything else on 58 here? Let's try 62. Yeah, Hans? That would be an even function. But we didn't integrate it over a symmetric interval. So that's why we're not using any of those results that we used last time. But if we look back here, let me zoom out a little bit. You can see that the function's a mirror image of itself around the y-axis. So if you were to fold things across the line x equals 0, the function would land on itself. So it's even. I mean, I guess I can look at this and say, oh yeah, that's even, because when you square something, you're going to get an even function, and cosine's an even function. So the product of two even functions gives you an even function. So a nice kind of follow-up remark to that is if I gave you something to integrate, like the integral from negative pi to pi of sine squared of x cosine of x dx, what could you do? Well, then you could, double the integral. All right. Okay. Let's try problem number 62. It's just kind of a quick problem, but it's got a neat little trick in it that I'd like you to see. So, problem 62. The integral of 2x squared plus 3x minus 2 over x dx. There is no quotient rule for integrals, period. Not even anything close. In section 8.2, we're going to get something close to a product rule for integrals. Close to, it's not really a product rule. But what you can't do with something like this is say, oh, well, that's the integral of the numerator divided by the integral of the denominator. You can't distribute that like that. But there is a nice little fix for our problems here. Break it up. You could break this up as 2x squared over x plus 3x over x minus 2 over x all dx. And of course, these simplify. That's just the integral of 2x plus 3 minus 2 over x, or how about 2 times 1 over x dx. And of course, you don't need anything fancy to integrate these. What's the integral of 2x? X squared plus 3x minus 2 times what? Natural log. Plus your constant. And that's it. One more little piece about this. And I've said stuff like this before, but I still get this kind of calculation. People will take this and do the same thing that we did. You can't split it up if you have multiple terms in the denominator. This is not equal to x over 2x squared plus x over 3x plus x or minus x over 2. You just can't do that. They're not the same. All right, but other than that, kind of a nice little trick to get yourself out of a jam and easy integration without having to resort to any kind of u substitution whatsoever. Well, one of the ways is with partial fractions, and we'll get that in like section 8.4. So basically, with partial fractions, what you're going to do is try and break things up. If I had, say, 1 over 4 minus x squared, I could break that up maybe into 1 over 2 minus x plus 1 over 2 plus x. And maybe that ended up being a 4 here. But these you can integrate using a log. So if you can somehow figure out how to break these things up, then you're going to stand a chance to integrate that kind of stuff. So, but that's coming up soon enough. Appreciate the question though. Thanks, Emil. So one last one from this section, and it's problem number 66. Deals with the function y equals 3x plus 2 over x squared plus 9. And they actually want us to find a particular area. So let me switch screens here real quick. And get rid of this one and replace it with this one. So there we go. We want to find the area underneath this curve between the points of 0 and 5 along the x-axis and above the y-axis, or above the line y equals 0, that is the x-axis. So this is simply going to mean we're going to integrate. So let's set that up. The integral from 0 to 5 of 3x plus 2 over x squared plus 9. So any ideas on this one? What would we do? I need my dx there. Any suggestion? Actually, this one won't factor because it's a plus. Yeah. So this is actually a prime quadratic. You can't factor this one, so you're kind of stuck with that in the denominator. You could do long division if the numerator were greater than or equal to the degree of the denominator. So it's another good suggestion, but doesn't work in this one. You are going to want to keep that idea around when we do partial fractions. And that is, if the numerator degree is greater than or equal to the denominator degree, your first step will be to divide. Well, let me go back and take a quick look at problem number 58. A lot of what you're going to do when you're doing your u substitutions is look for part of your function which is a derivative of another part. Like cosine is a derivative of sine. So, okay, how does that apply here? Well, when you think of differentiating a polynomial, what happens to the degree of the polynomial when you differentiate it? Drops by 1, right? So that's kind of a little bit suggestive because you've got a second power here and a first power here. So, okay, here's what I'll do. I'll split this up as 3x over x squared plus 9 dx. And then I've got the integral from 0 to 5 of 2 over x squared plus 9 dx. Does that help me out at all? Yes. It helps me out in two ways. What are we going to do to integrate the first one? Yeah, u substitution. How about the second one? Does anyone recognize what's going on, what we're going to have to do with the second one? Arctan. Good. So we're going to have the arctan on that one. So for our u substitution, let's see, we're going to let u equal x squared plus 9. Du would be 2x dx. Now, I've got an x dx here. I'll pull the 3 out in front of the integral and deal with it that way. So I'll get 1/2 du equals x dx. And like I said, it's my habit that I solve, or I change the limits of integration. So let's see, u of 0 would be 9, and u of 5 would be 34. So my new limits, and I'm done with the x's at this point, my new limits are 9 to 34. And that just comes from plugging in the values of x in here. And I'll have, what, 1/2 du over u. Okay, so making some good steps. Let's see here. The 3 and the 1/2, that's a constant, so that'll come out front. 3/2 times the ln of u. I'd use the absolute values, but my limits here are going to be positive anyway, so I'm not going to bother. 9 and 34 plus 2/3 the arctan of x over 3 between 0 and 5. Let's keep going. So that's going to be 3/2 times the ln of 34 minus the ln of 9 plus 2/3 times the arctangent of 5/3 minus the arctangent of 0. There's not much in terms of simplification that I would be looking from you on a problem like this. There is one thing that simplifies pretty nicely. Does anyone see it? Arctan of 0. What's the tangent of 0? 0. So the arctan of 0 is also 0. So that disappears. That's just a big 0. You know, if you were to look up your answer in the back of a book or in WebAssign, they probably wouldn't write it like this. I'd accept this on an exam. That's fine. But they're probably going to use the quotient rule and write it as a ln of 34 over 9 plus 2/3 the arctan of 5/3. So, yay. Nice ordinary household number, right? Probably use it a dozen times, balancing your checkbook or something like that. All right. How are we doing with 66? Just a couple good examples of some of the integration techniques that you're going to need. Nothing really outlandish, I don't think. Okay, well, that's all I wanted to do for section 8.1. So like I said, there's a couple bonus problems. And I think I assigned the homework last week, right? Did I get you up to problem 65? Okay. All right. So we're good.